Hello everyone, myself Shahed, and today we'll be discussing about ternary search. So just like the binary search, ternary search is also a divide and conquer algorithm, and just like the binary search, it also needs an sorted array to execute its search. But in binary search, we saw that the array gets splitted into two parts, but here the array is being splitted into three parts. And the time complexity of the ternary search is big of log 3 base n. So moving on, we can see that here is an array of 12 elements and the index are going from 0 to 11. So like if there's 12 element, we start indexing from 0, so it will go up to 11. So to split this array into three parts, we need to find out two mids, mid 1 and mid 2. But unlike binary search where we are like just dividing the arrays into two parts, there's a little bit more than that. So to find out the mids, like these are the formula for mid 1 and mid 2, and this mid 1 and mid 2 will help us to split the array into three equal parts. So first we have to see what is this L and R. So normally the L is the leftmost index, or in the beginning it's gonna be 0. So you have to assign L as 0. And then the R is similarly the rightmost index, or length minus 1. So as I said, there are 11 elements. So if you find out the length of this array, then it's gonna be 12. So 12 minus 1, that's the index number 11, and that's gonna be your R. So that means this L and R, using which we're gonna find mid 1 and mid 2. Both of them are index numbers. So the mid 1 and mid 2 that we're gonna get is also the index number. So now let's go dig a little bit into this mid 1 and mid 2 formula, because like if you have to memorize the formula now, then it's a little bit risk. First of all, why should we need to memorize the formulas? So I'm gonna explain these formulas a little bit so that you can just come up with the formula even if you forget it. So firstly, this part here, R minus L divided by 3. This part, so this is like the right side minus left side divided by 3. So when we're doing right side minus left side, so that's the length of the array. So that's the rightmost minus the leftmost. And you have to keep one thing in mind, these are index numbers. So we're gonna be doing our calculation with respect to this index logic. It's gonna start from 0, not from 1. So when you're doing right minus left, then it's gonna be 11, 11 minus 0. The answer is 11. But there are 12 elements in the array, but we are getting the length as 11. But if we're thinking about as this is 11 in index, then it is correct. We are starting from 0, then we're going up to 11, so we will have 12 numbers. So in that logic, in that way we are doing it. So right minus left divided by 3. So if we're dividing the length by 3, so that we will get 1/3 the length, or the index number of 1/3 of the array. So from the beginning to that number, that's the portion of one segment, 1/3 of the array. So to get the mid one, what we're gonna do is from the left portion, we are going this R minus L divided by 3. This is 1/3, the length of 1/3 of this array or any array. And we are from L, we are going that portion inward in the array. So we are from L, we are adding R minus L divided by 3. And that is our mid one. And that means from L, which is 0, to mid 1, we are getting the first segment of the total 3 segments of this array. So similarly, for mid 2, we are taking R minus L divided by 3. That's 1/3 of the array. Then from the right side, we are going inward 1/3 of the array inward to get our mid 2. So that's why we're doing right minus left divided by 3. And that will be our mid 2. So that means from mid 2 to R, or the ending of the array, we are getting the third segment, which means we only have one portion left. So this one portion will be the second portion of the array. That means we got, using this mid 1 and mid 2, we segmented this array into 3 equal parts. Then, okay, let's find out the mid 1 and mid 2 for this specific array. So when we're doing, one more thing here, when we're doing this division, like R minus L divided by 3, this is a floor division. So as we can see here, 11 minus 0 divided by 3, that is 3.667. And we are taking the floor of it, 3. So 0 plus 3, it becomes 3. Our mid 1 is 3 number index. So 3 number index is our mid 1. And then for mid 2, R is 11. 11 minus 3, which is 8. So 8 number index is our mid 2. So that's how we just divided the entire array into 3 parts. So normally what's gonna happen is they will give us a key to find in the array. So let 10 be the key which we need to find. So what's gonna happen is, like, they will give the element to you and you have to find the index number at which that element is situated in the array. So your output going to be an index number, not the element. Like, this is a common mistake that people do. Instead of giving the element the index, they give the element itself as the output. So we have to give the index number as the output. So we have mid 1 and mid 2. Now, when we are given a key, the first thing that we're gonna do is check that array mid 1 is equal to key. That means in the mid 1 index of the array, the element that is situated, is it equals to the key? If it is, we will print the mid 1, which is the index number. So if we see in the above array mid 1 is 8, but our key is 10. So that means this condition is not satisfied. So what we're going to do is, we're going to similarly check if array mid 2, the element in mid 2 index, is equal to key. So here we can see that in the mid 2 index we have 22, which is not equals to key. So if it was, then we would have printed the mid 2 index number. Since it isn't, then we have to go down to the further conditions where we're gonna check where this key, the key that is given, might be situated. So the first condition that we're gonna check is if the key is less than array mid 1. If it is, then we're gonna do right equals to mid 1 minus 1. What this gonna do is, it will bring this R all the way one index ahead of mid 1. And that means, if you look at it carefully, then you can see that at first our searching length was from 0 to 11, and when we're bringing the R all the way to 2, now our left is 0, right, and right is a 2 number index. So we are reducing the array's length, or our searching field, by a substantial amount. But in this case, our key is 10 and our array mid 1, it is 8. So 10 is greater than 8. So this condition is not satisfied. So next we're gonna check is if the key is greater than array mid 2. If it is, then what we're gonna do is L equals to mid 2 plus 1. That means this L will be brought all the way here, mid 2 plus 1. So one index after mid 2. But in this case, the key is 10, our mid2 element is 22, and it is said if the key is greater, but the key is smaller. That means we have one other case left, which means this key is situated in between mid1 and mid2, and which we will write in the else condition. And here we see that both our L and R are getting modified. So what is happening is L is mid plus 1. So this L is going one index after mid 1. Your R is mid 2 minus 1. So R is coming one index before mid 2. So now our L is here and our R is here. So for the next recursion or loop, like it depends on you how you are coding this ternary search code. So if you are doing a recursive code, then like for your next recursion, if you're doing a loop, then for your next loop, your array is reduced down to this much. So we actually, like if you see 1, 2, 3, 4, 5, 6, 7, 8. So we literally reduce the array search field by reduced it down to 1/3. We remove 2/3 of the array with one iteration, which is why like this search method is slightly faster than binary search. So now taking our L as 4 and R as 7, we will find our mid 1 and mid 2. This is the value. You can do the calculation yourself. I hope so. Now what you're gonna do is same. We're gonna check if array mid 1 equals to key. It is 13. It's not equals to key. Then we will check if array mid 2 equals to key, which is not. It is 16 and the key is 10. So then we're gonna check is the key is less than array mid 1. This is mid 1, so array mid 1 is 13 and our key is 10. So key is less than array mid 1. That means this line will be executed. Right equals to mid 1 minus 1. So what is gonna happen is this right is going to come one index before mid 1. But here we can see is our left and right, both of them are in the same element or same index. Which means what is happening is now our array is reduced down to one singular element after our second iteration. So when it's down to one singular element after like multiple iteration, that's your worst case scenario for ternary search. Like you have to search the entire array up until you have one element left. So there is two things that can happen here. Either that one singular element is your key, or that one singular element is not your key and the key given does not exist in the array. But for both of these scenario, you have to come down to one last element, which is the worst case scenario. And here we can see that we are seeing the worst case scenario. We only have one element left. So if we do like find the mid 1 and mid 2 for this case, then we can see that here is the calculation. Both of them are coming 4, 4, because we only have one index. Our L and R, both of them are 4. So then we're going to check is array mid 1 equals to key. We only have one element, so the condition will check. And we will print out mid 1. So the answer is index 4. So that's our answer. And that's how we can find an key using ternary search method from an array. So now we will look into the time complexity of this searching method. So for time complexity, one thing you have to do is you have to consider the worst case scenario. So like as you can see here, like we are down to one singular element after multiple iteration of our algorithm. So this is the worst case scenario. So for this kind of scenario, not like this specific. Like this is the worst case scenario for this array, but like normally like there could be an array with 200, 300 elements. So like there will be like, let's say 10, 12 iteration. So here we like got the single element after like the second iteration, but like normally we are like doing these searches on like a way bigger array. So they're gonna be like more than 10, 20 iterations. So we have to keep that in mind. We are like finding out like the time complexity for a general case, and for the worst general case, like where the array size could be like very long, and the worst possible scenario, which is down to one last element. So for finding out the time complexity, we have to do this relation, number of steps and number of elements. So first, in like this number of steps, also like you can call it as like how many times we have executed our algorithm. So when we didn't execute our algorithm even once, the array had, let's say the array had n number of elements. So the number of elements that we have in our hand is n. But after we executed the algorithm once, as we can see, we like take 1/3 of the array and we discard 2/3 of the array, like as our search field. Like we do not like modify the array, we just reduce the search field to 1/3 of the size of the array initially. So that's why the number of element in our hand is n divided by 3. Then when we execute the array once more time, it's n divided by 3 divided by 3. That's how it's n divided by 9. Then if we execute the array one more time, it's n divided by 9 divided by 9. That's n divided by 27. So let's say after k number step, we found our answer. So like after k step, we went down to one singular element, and that was our answer. But in terms of this n relation, like how can we find that like in this kind of like n term for k? We have to find that out first. So if you look here closely, there is a pattern here. The pattern, which is more likely n divided by 3 to the power 1, n divided by 3 square, n divided by 3 cube. And similarly, we can write n equals to n divided by 3 to the power 0, which is 1. So if you look at the power, the exponentials, 0, 1, 2, 3, these are the number of steps. So for k number step, we can write it is n divided by 3 to the power k. Now, as we said, in worst case scenario, when we find our answer, we have to go down to our one last element. And we said in k number step, we found our element, and that's why the algorithm stopped and there is no more steps after this. So the value here, like this n divided by 3 to the power k, the number of element that it equals to is 1. So we will take this relation here and we will work on it, because from this relation we will find k equals to something in terms of n, and that's something going to be our time complexity. So first we can do is multiply both sides by 3 to the power k. So now we get n equals to 3 to the power k. Then we are taking log 3 base n on both sides. And the reason for this is explained in the next line, which is there is a formula of logarithm. Log base n, n to the power k equals to k. K is the power here that the n has. So in this case, we can see that 3 to the power k, we need this k to equal to something in terms of n. To get this k, we multiplied both sides with log 3, because we have 3 as the integer here. So 3 log 3 base 3 to the power k. According to formula, we will get k, and on the other side, it is log 3 base n. We can also write it as k equals to log 3 base n. So now this is our time complexity for ternary search, big O of log 3 base n. And this from this time complexity, we can tell that the ternary search is slightly faster than the binary search, because binary searches time complexity is big O of log 2 base n, which is why ternary search was invented in the first place, because it was giving us slightly faster time than binary search. So this was it for this video. Hope to see you guys again in another video. Until then, take care.